All right, so welcome back, everyone. So in the last lecture, we essentially computed the Lyapunov index associated with this black hole geometries, and we saw that it saturates the bound. That's what we discussed earlier. And the way we did the computation was to compute boundary OTOC in the bulk using holography, and it turned out to be a 2-2 scattering type of thing, right? Now the computation was quite involved, and some of the intermediate steps was like cannot be readily generalized to higher dimensions. That was one of the limitations. Okay, so in this lecture, what we are going to do is I'll try to present an alternate description of chaos, which essentially emerged from the study of SYK model, which also saturates this chaos bound, like black holes in Einstein gravity. Okay. So in the first 5 to 10 minutes, I will give you the story of chaos in this SYK model. And then for the rest of the lectures, we'll try to replicate the story in Einstein's gravity. Okay. So SYK model, as we know, is a one-dimensional model of Majorana fermions. Psi A, del T psi A, some 1/4 factorial. So this first part is like conformal quantum mechanics, but then you turn on this interactions. I mean, so this is like all-to-all interaction, but here I've written 4 fermions interacting at a time. And the coupling, these are some random variables drawn from a Gaussian distribution. Okay. So the model is essentially parameterized by 2 parameters. One is the number of fermions, and the other is this dimensionless coupling. So where this J is the variance of this JABCD, and this has a dimension of mass, so the dimensionless coupling is something like this lambda, which is J over T. Okay. Now, the larger limit of this model is classical and is exactly solvable for any lambda. Okay. Now, we are particularly interested in the regime where this lambda goes to infinity or T goes to equivalent to 0. Okay. This is a strong coupling regime. Now, it so happens that in this regime, the model essentially enjoys an emergent conformal symmetry. So this symmetry is otherwise present in this whole action, I mean, due to this interaction, but however, in the strong coupling regime, the symmetry emerges. Okay. So, this as so if you consider this line, say T equal to 1 over lambda and T equal to 0, so you have a CFT1 fixed point. Now, Maldacena and Stanford, they essentially computed the OTOC of the fermions in this regime, and they found that it saturates the chaos bound. Okay. Right. So the question is, how did they get this? I mean, obviously, we are just in one dimension, there is no scattering and things like that. So the story of chaos and SIP model goes as follows. To extract this Lyapunov index, what they do is first to slightly zoom out of this conformal fixed point. That is like saying turning on a small temperature. Okay. So near this conformal fixed point, this SYK action can be roughly written as CFT as lambda inverse as Georgian. Well, the Georgian is the Georgian derivative of this time reparameterization. Okay, taken. So you can see that just you slightly move away from this conformal fixed point, your conformal symmetry gets explicitly broken to SL2R. which is the symmetry of this action. Now, due to the breaking of this symmetry, some of these time reparameterization modes, they become dynamical, and the dynamics is governed by this Schwarzian action. Okay. So what they found essentially was that is the contribution of the Schwarzian modes, which we call the soft modes, to the 4-point function, that essentially leads to this exponential behavior. This is a subleading contribution, but this ultimately leads to this exponential lambda t kind of behavior, which saturates the bound. Okay. So this is more or less the summary. So you have a big symmetry, you break the symmetry, some of the modes become dynamical, and you study the contribution of these dynamical modes to the 4-point function, which is subleading contribution. But is this particular contribution that goes on to saturate the bound? Okay, so these are like some fermionic external links. So this is roughly the, the one slide summary of this chaos in a spiky model. So now, since black holes also saturate this bound, so we want to understand whether there exists such an analogous Schwarzian description for chaos in the black holes. Okay. So the question that we'll address is, Schwarzian description for black holes. Right. So more technically, the question is like, what are the soft modes here, and where do we actually find them? Okay. Now, level 2 question is, if we are able to find such kind of a description, then does it somehow relate to the shockwave picture? Sorry. Right. So these are primarily the question that we address here. So now let us to address this question. How do you address it? So first, let us go back to our old picture. So essentially what we did, we sent in two pulses came out, they interacted near this near horizon region, and that essentially led to this exponential growth here, right? So if we are after certain chaotic dynamics in this black hole geometry, this is the essentially should be our region of interest, because it's the interaction in this region that essentially lead to this exponential behavior. Okay. So that's like a first hint. The second thing is that now if you try to relate to SYK model, here the chaos was actually a near extremal phenomenon, at small temperature. So if you try to relate to chaos, we must think of the black hole near extremality. Now, when you are near extremality, this near horizon region is actually a ADS2. Okay. So let me draw this thing. So suppose you have a black hole, and this is a horizon. Right. Now, if the geometry is close to extremality, there exists a throat region near the horizon where the geometry is like ADS2. Okay. So in some sense, our problem boils down to studying dynamics in this ADS2. Okay. So let's start with that. So let's start with, for example, Einstein gravity into Einstein-Hilbert action in 2 dimensions. Okay. So it's like 1/16 power chain between GR H2. Now, if you nicely vary this action, the equation of motion that you'll get is R mu minus equal to half G mu R. However, this equation is nothing but all it's saying is like R equal to R. Okay. It's not a dynamical equation. Any 2D metric will solve this equation, even if you do not know explicitly. So in ADS2, there's actually no bulk dynamics there. That's one thing. The other thing about peculiarity about ADS2 is that now suppose you say I add matter to this. So can we study the dynamics of the matter? Well, now if you vary this action, the right hand side you get T mu nu, but since the left hand side still vanishes identically, I mean, it forces your T mu nu matter to be zero, which is like saying that ADS2 does not support finite energy. This is actually very easy to understand from the dual perspective, because see the dual of ADS2 is actually CFT1, which has one component of stress tensor, right? Say TTT. Now, tracelessness will impose that this component must vanish, right? So CFT1 is like energy is exactly zero. Now you cannot add anything to a system with zero energy and say that it is, I mean, because if you add anything small but finite, then your energy is essentially no longer zero, you're no longer CFT1. Is there a question?
Yeah, I couldn't understand this thing. When you have a T mu nu, then why still the left hand side is zero? That I
Left hand side is identically zero. I mean, this is identity that always works. I mean, in 2 dimensions, I mean, any metric is.
Well, in 2 dimensions, you can write it as some this anti-symmetric combination of the metric, right, with some normalization. That is the most.
Sorry.
In 2D, the
Yes.
R mu nu isn't it?
I mean, there is actually no Einstein's equation. Okay. So the variation of the matter action with respect to metrical set it to be identical is zero. This is nothing. This is just saying R is equal to R. There is no diametric Einstein equation in 2 dimensions. So at matter, I mean, this stress tensor will identically vanish.
And this you are saying is only in the case of 2D.
Yes, this is 2D. This is only 2D.
Okay.
Yeah, so the way to understand is that the dual safety, the stress tensor identically vanishes because it's CFT. So if you add anything small but finite, then it's no longer a safety. Okay. So this also goes by the name of this back reaction problem of ADS2. So matter back reaction always destroys the asymptotics of ADS2. Okay. So I mean, you can also say things like the ADS2 only has irrelevant deformation. So suppose you have an ADS2, I mean, it's like a CFT1 in terms of the RG flow. You at any perturbation, it will start flowing along some irrelevant direction, and soon you will go out of ADS2. Okay. So because of these two reasons, there is no bulk dynamics, and of this ADS2 only has irrelevant deformation. Under the flow, it always goes out of ADS2. It's actually more instructive to think of this ADS2. I mean, think of ADS2 as coming from some IR, a low energy limit, of some UV geometry. Or saying in other words, I mean, it's more instructive to talk of cutoff ADS2 than pure ADS2. Okay. So what's the advantage we'll see shortly? So what is this cutoff ADS2? So ADS2 is like a, so we will work in Euclidean, I mean, for the time being, since ultimately we are interested in correlation functions. So Euclidean ADS2 is like this hyperbolic disk. Okay. Right. You can also, for example, use Wheeler coordinates, sine hyperbolic square root square. Now, in Euclidean, both these coordinates actually cover the whole hyperbolic disk. Unlike in Lorentzian, where they essentially will cover different regions. Okay, this in Lorentzian, this in Euclidean. So when it is the Euclidean picture, so we'll essentially use both, I mean, either as required. Okay. So now what we want to do We want to cut off this space along some arbitrary curve. Okay. So for example, beyond this cutoff, the geometry is something UV geometry that we don't know, we don't care of. So suppose the time of this UV geometry is U, which will take to be the boundary time. Okay. And in the interior, we have a ADS2, where my coordinates are like T or Z. Okay. Now, we can parameterize this cutoff by these two functions, T of U and Z of U. Okay. So one is like related to the shape of the cutoff, and the other is like the length of this boundary curve. Okay. Now, the length of the boundary curve typically diverges as you approach this boundary. So what we'll do, we'll essentially put a UV, I mean the cutoff on the length of the boundary. Okay. So if you look at this metric, this now in terms of this, the boundary metric now becomes C prime square, Z square, TU square. So this will diverge as Z goes to 0. So essentially what we'll do, put a cutoff here on the length. So for example, now the length is on 1 over lambda. So now when you fix the length, then you can solve this equation. You find that ZU and TU are no longer independent. It's essentially given by prime plus some other. So now from this 2 degree of freedom, you are just down to 1 degree of freedom TU, which is like my shape degree of freedom, because even if I fix the length of the curve, I can choose arbitrary shape which still have the same length. Okay. So in this way, you have actually, by choosing different TU, you essentially have different geometry, I mean different cutout. And this in some sense generates a family of solutions, because see, locally these geometries are all, I mean this ADS2, but suppose you have make some non-local observation measurements like some 2-point function and so on. That will depend on this, I'll show later, that will depend on the shape of this cutoff. Okay. So in that sense, these geometries are all different geometries. So we have a family of solutions. Another thing is that now suppose I can do some boundary time reparameterization. So you're going to U tilde U, under which the shape will go from T of U to some T tilde U tilde U, say it's on T tilde U. Okay, so just by doing a boundary reparameterization, we can now go to one geometry to other. So just to avoid, I mean, various clutter of notation. So my U to TU will be like a reparameterization. And also like going from one geometry to other. Okay. So thus we have actually generated, by just by cutting out, we have generated a family of solutions. Okay. Well, I should mention that there is an alternate point of view to this. So this family of solutions can be thought of being generated by the large diffeomorphisms of ADS2. Okay. So these are some large diffeomorphisms of ADS2 which respects Dirichlet boundary conditions. So when you act it on, say, on this Euclidean ADS2, you promote it to this family of solutions, which is characterized by this function f of t. So as you can see, the leading part of the metric is same, so it respects Dirichlet boundary condition. And this is also large because, see, as you approach the boundary z going to 0, then it essentially boils down to a t going to f of t kind of transformation, which in our language is like u going to t of u. Okay. So to summarize these two point of views, so essentially the difference is that where you have your degree of freedom. So in this picture, my degree of freedom is like in the shape of this geometry, but my internal geometry is fixed. Whereas here, my boundary shape is fixed, but internal geometry now has this dynamical degree of freedom. But in either case, my degree of freedom is actually a boundary degree of freedom. So TU or FT. Now we're working with this, but maybe later we'll comment on this. Okay. So my degree of freedom is actually a boundary degree of freedom. So we'll call this TU our boundary degree of freedom. Okay. So just by cutting out, we have now some dynamical degree of freedom. Yeah, go on.
Yeah, means could you explain? Means this U going to TU or TU doing a reparametrization. Why is it not general coordinate invariance, and why it takes you from one geometry to another geometry? That can you explain once more?
Sorry, his voice shaked a little. Can you repeat?
Well, means you are basically you are changing, doing a coordinate change, right?
Yes.
So one would expect in gravity that just a general coordinate invariance of your theory, and not you're not changing the geometry. That's something one would like normally expect. But here, how do you show that this is like going from one geometry?
I'll show you. I'll show you the next. That's what I.
Oh, okay. Oh, okay. Thank you.
Yeah. Is there anything other question? Okay. So yeah. So now by cutting off, we now have a dynamical degree of freedom. So can we study the dynamics of this graviton within Einstein-Hilbert action? But the answer is that no. Why so? Because you see, this ultimately this ADS2 is like a hyperbolic disc. Okay. So and we are cutting out various shapes out of it. And various shapes are like various geometries. Okay. Now, for Einstein-Hilbert action in 2 dimension, the action is nothing but related to the Euler characteristics of this 2D manifold. Okay. So whenever this cutoff is like a simply connected chunk of the disk, it essentially has same Euler characteristics. Okay. So all these TUs are symmetry of the action. I mean, by no way you can actually study dynamic beat bulk or beat boundary. Einstein-Hilbert action is good for nothing in 2 dimensions. Okay, so all these TUs are symmetry of this action. So there is essentially no dynamical mode within Einstein-Hilbert action. And for example, I mean, this now you can relate to the boundary as the invariance under T going to TU, which is like my CFT1 symmetry, right? So symmetry in the boundary is like a invariance under time reparametrization, which has I mean, so Rithobrata's pointing is like a gauge symmetry, right? So within Einstein-Hilbert actions, all these TUs are same, and this is indeed like a gauge symmetry, C1 to T of U. Okay, does that answer you, Rithobrata?
Yeah, okay, so it is basically a diffeomorphism.
Yes, I mean, it's actually a boundary reparametrization, and within Einstein-Hilbert action, these are trivial.
Okay, yeah, okay.
So now at this point, let us check how are we going with SYK model. So how are we keeping up with SYK model? So, okay, sorry. So this Einstein-Hilbert part of the action, this is much like this SCFT of SYK, right? But all this time reparametrization is a symmetry. Now, in SYK, so to get this Lyapunov behavior, what we had to do is slightly had to zoom out of this conformal fixed point, right? Which essentially broke this infinite symmetry, okay, and made some of them more dynamic. So what the knowledge of SYK is saying now is that we have to add something to this action, something. So which will break this reparametrization invariance and make the sum of the modes dynamical. So one thing is that it breaks the reparametrization invariance. Another thing, I mean, again, keeping up with SYK, so it's supposed to take us away from this extremality. So far, I've been talking about exactly extremal black hole, the near horizon is ADS2. So this, whatever they add, it's supposed to take us away from this extremality like this. SYK. Okay. And the object is this JT. So now what I'll do, I'll actually justify my claims. So first, I'll show you by explicitly deriving this JT action that it essentially takes you away from this extremal point like SYK. And the second thing I'll show you that indeed breaks this reparametrization invariance. Okay. So how do you derive this JT action? I mean, for this near horizon geometries. So you start from your Einstein-Hilbert action in higher dimensions, and this essentially holds in any dimension, the story. Okay. So for example, here we consider 3 dimensions. And you first now consider a saddle of this geometry, I mean, this action, which is, for example, we take this rotating BTC. You can actually work with the non-rotating BTC, but it's fine. I mean, I've chosen for a more general BT. Okay. So now you take the geometry and you take the near horizon limit at extremality, which is essentially given by this. So your R plus equal to R minus is extremal, and your near horizon is given by this parameterization. Okay. So now if you look at this geometry in this limit, you have, this is the ADS2 throat you have. Okay. The full geometry is something like this, but then you have this ADS2 throat near horizon. Okay. So what we want to do, we want a dynamical action for this near horizon geometries because Einstein-Hilbert action is not good enough. Okay. So now to get an action, you have to promote this geometry to a family of solution first. There's no action for a single geometry. So you essentially choose this answer. So you promote this 2-dimensional part to this the metric in 2 dimensions. And this phi square, this is the extremal. So this is like the horizon radius, which you now promote to a function of r comma t. So this is like this dilaton. And this standard Kaluza-Klein type reduction. Okay. And this is like some gauge field. Okay. Also at this point, note the extremal value of this field. I mean, this dilaton extremal value is r plus, and this gauge field extremal value is this. Okay. So now if you reduce your Einstein-Hilbert action based on these ansatz, then this is what you're going to get, a 2-dimensional nice action. Okay. But still, this is not, I mean, now you have this additional field. So we want an action which only has this dilaton and the metric. So we'll go on shell with respect to this F. So essentially solve this equation of motion for F. And the solution is very simple. This is like the integration constant Q, okay, which you can fix from this extremal value. All right. So now you put this value back in the action. So this is like a dilaton gravity action. I mean, also there is a kinetic term for dilaton that comes, but you in 2 dimensions, just by using while invariance, you can kill it off. Okay. So this is like a 2-dimensional dilaton gravity action. Now let's look at the action at the extremal values of the dilaton and also this Q. In that case, these 2 terms will exactly cancel each other. So this is coming from 3 dimensions. So lambda is now 1. So this 2 and this 2 will exactly cancel each other, and you recover your Einstein-Hilbert action. Okay. Yeah, go on.
Can you again tell me how you're putting this FRT solution? I mean, from the 4-dimension or 2-dimension? A 3-dimension or 2-dimension?
I'm coming from 3 dimension. This is my answer.
Then you went to 2, then
I'm reducing along this isometric direction X.
right.
So this is the action that I get.
Right, yes.
So now what I want the action for my dilaton and the metric. So I will
Right.
go with respect to F. So you can simply solve the equation of motion for F, right, from this action.
Okay. You are going on shell for the F only. I mean, the gauge.
I want an action for my metric and
only dilaton and graviton. Okay.
so it is this. You solve it. I mean, there's an integration constant.
Okay.
Yeah. So what is said is that so when you take the dilaton to its extremal value, your action is the Einstein-Hilbert action, which will show that there's like this extremal, I mean, the CFT1 fixed point of this Viking model. Okay. So now to get JT gravity, what you have to do, you have to slightly move away from extremality. And we choose this phi to be much less than phi extremal. Okay. So when you put these answers in this action and you linearize in this phi, you will essentially get this JT action. So JT action by derivation takes you away from extremality. Now, if you look at this JT action, it is supported by this departure from extremality, right? Okay. So now we have moved, this JT action has taken away from extremality, like this is YK. So kind of picture. Now we want to see, does it break this reparametrization invariance of this Einstein-Hilbert action? Okay. For that, sorry. So just look, we have to just analyze the equation of motion of JT. So for example, the phi equation of motion is very trivial, is saying it's AD is 2. And then this Dilaton equation of motion is given by this. So now in this AD is 2 geometry, you can actually solve this Dilaton equation of motion, which is given by this. Now both diverges, as you see, that both diverges as z goes to 0. So this is a generic pattern of AD is 2. All the fields will always go towards this UV. I mean, metric obviously goes, but even the dilaton, it has a growing mode. Okay. So again, what you do, you just cut off your space and you impose some dilaton boundary condition on both the metric and this. So as we saw that if you impose the dilaton boundary condition on the length, I mean on the length of the curve of this metric, then essentially you have 1 degree of freedom. Now, furthermore, if you specify this, then that also kills this t degree of freedom. But we don't want this. Okay. We want to keep this tu as my dynamical degree of freedom. So what we'll do, we'll essentially evaluate this action on shell with respect to this condition only. We'll not refer to dilaton equation of motion at all. Okay. Because then we do not have any degree of freedom. So when you impose that in this action, the on shell action you have on this term, okay, this boundary term. And if you evaluate the extrinsic curvature, for example, of this curve, again, I'm in ADS2 and I'm also only interested in cutoff version of ADS2. So if you evaluate this extrinsic curvature of this cutoff, I mean, on this solution, then you essentially see that your action is nothing but this JT action is nothing but it's on shell with respect to this metric only, not dilaton. Okay. It's nothing but a Schwarzian derivative, which is exactly what SYK model has. So this is like the Schwarzian derivative of this time reparametrization. So again, the symmetry gets explicitly broken to SL2R by this JT term. Okay. I call it explicit breaking because in this case, the breaking is at the level of action. Okay. On the other hand, suppose I mean in the earlier case, what we were discussing is various cutoff. You choose one particular cutoff that also breaks this reparametrized symmetry, but there's a spontaneous breaking because there's the symmetry is broken at the level of solution. Okay. But here I'm breaking the symmetry at the level of action. So there's these two things, this explicit breaking and spontaneous breaking, and this breaking pattern is exactly similar to what happens in this spiky model. For example, there this choice of this saddle of this, I mean, okay, let me not go to that. So here we have two pictures of symmetry breaking. One is explicit, which is at the level of action. The spontaneous breaking will not talk much about breaking. So now what happens is that now my u going to t of u, when this t of u is SL2R, this actually does not give me any new geometry because the action is 0. Okay. So this SL2R is in some sense now my gauge symmetry. It's not relevant. Whereas the transformation where this t is not SL2R, those are my relevant transformation because now they take us from one geometry to other. But this is a consequence of this JT gravity. Okay. I'm not talking about Einstein-Hilbert action. For the Einstein-Hilbert action piece, every TU going to TU is like a symmetry, but when you have this JT or the Schwarzian, only this SL2R symmetry you have now, and rest all are like. So in this case, our soft modes are like this boundary gravitons. Sorry, it's too small for it. So at least we have identified our soft modes here. Also, okay, so now again, just so what happened here is that, so essentially we're sitting, so when this dilaton is at extremality, so you sit at your, say, CFT1 fixed point where Einstein-Hilbert action, all requirement transition symmetry. But now you turn on a fluctuation of this dilaton and it essentially grows towards UV, right? That's what we saw. So at some point we cut off the space where this boundary value of the dilaton is still much smaller than this phi extremal. So this is what is known as a near extremal setup. So at this point, you only have preserved SL2R. Okay. As you move. And so at this point, you essentially have your dynamical soft modes. So it's just like moving away from this CFT1 fix, but exactly what happens in this one. Right. So I'll just pause here for a while. I mean, if there is some question, otherwise I'll move on. Okay, if not, so now that
Hi. So can you explain that how SL2 are becoming gauge symmetry?
well, in the language of CFT, this is still a global symmetry, okay. But in the language of this gravity, it's a gauge symmetry because my U going to T of U does not give me new geometries or new solutions because the action cost is 0. Okay. I mean, this is like my, I mean, this is a redundancy. This is SL2R. So it's actually called a global gauge symmetry in this language, JT language.
Okay.
Okay, so now that we have got a Schwarzian theory, the rest part is actually, so what we'll do is now find a saddle of this Schwarzian theory. Saddle means like finding which of the shape actually extremizes this JT action. Right, so then we'll essentially fluctuate around the saddle and compute the 2-point functions of this gravitons. Okay. And finally, we'll find the contribution of this propagator, this soft modes to the 4-point function and see what happens, right? So now to find the saddle of the Schwarzian theory. So if you vary this action, this is the equation of motion you get. Okay. And if you integrate this equation of motion, you essentially get back to the same equation of motion that you got from this JT gravity. So the equation of motion from boundary action is exactly the equation of motion that comes from bulk action. So this Schwarzian action essentially captures all the features of this bulk. Okay. So now suppose we want to find the saddle for this constant value of this dilaton. Okay, this is just a simplification. So when suppose we set it to 1, then for example here, if you just constant comes out, then you can cast this remaining equation of motion as a derivative of this Schwarzian. I mean the Schwarzian transformation. I mean the Schwarzian is a derivative of this Schwarzian derivative. Okay. And the most trivial solution is like u equal to u, because in that case the Schwarzian derivative itself vanishes. And this is like your zero temperature saddle. Okay. However, since we are interested in a picture like chaos, we'll be interested in a thermal saddle. So for that, we'll essentially switch over from Poincaré to this Rayleigh coordinates. Sorry, this is tau. T of u is tau of u. Now, under this transformation, this equation of motion becomes something like this. This is the Schwarzian transformation property. And now you can see that if this tau is a linear function of u, then this part is a constant and this part vanishes. And the derivative of this constant is 0. So essentially, this is my solution. So in terms of this Tu, my thermal saddle is something like a tan of pi by beta. So you take this beta going to infinity limit, you get back your U. So this is my thermal saddle. And my action, JT action now under this time, I mean this time redefinition, I mean this going from Poincaré to Rayleigh, this is my action. Okay. So now what we'll do is essentially fluctuate around this saddle. Where this beta is equal to 2 pi. We have chosen, we'll restore it later. And now since we are interested in the propagator, we will consider the quadratic action coming from it. So the quadratic action is simply, so let me call this entire factors and see. So this quadratic action is something like this. Okay. So now we want to quantize these modes, say on a thermal cycle. epsilon n. Okay, so these are my modes now. So if you now evaluate the action on this, then what you get is sum over n, n square minus 1, epsilon n, epsilon minus n. So now you can essentially read off your propagator to be, sorry, it was c over 2, so it will be some 2 c I nu. Okay. So this is my propagator for this graviton. Now here two things we must note. First thing is that here this propagator has poles at n equal to 0, plus minus 1. Okay. But in terms of mode expansion, these are nothing but my SL2R modes. These are SL2R modes on the circle. Okay. This A plus B to the power u, C to the power minus I. So essentially, I just seen that these are nothing but redundancies. So we essentially drop these solutions. They do not give me new solutions, so we'll just drop them. That's the one thing. And the second thing is that this will use that this epsilon is actually, this propagator actually symmetric with respect to u going to minus u. This is actually equal to epsilon minus u epsilon 0. Because we can absorb this in n and then it's going a square. So yeah, it's symmetric. How do you compute this propagator? And it's very simple. It's just the standard trick. So solve this Matsubara sum. As a contour integral. This is a standard trick to evaluate this Matsubara sum. So one typically writes this as some contour integral ds. Okay. But this contour now is like union of all the circles around integers except for 0 and plus minus 1. Okay. So we can essentially write this contour again as, draw the contour in the following way. So suppose this is 0, this is plus 1, this is minus 1. It goes all the way to infinity. Okay, just doing this. Right. Now what we can do, we can essentially define this contour as a small contour which encloses only these 3 redundant solutions and a big contour at infinity. Right? That's very trivial. Now the next thing is that if you look at the propagator, yeah, I should copy this. If you look at this integrand, yeah. So in the upper half plane, the contribution from this large circle essentially drops for u greater than 0, right? And in the lower half plane, the contribution can be dropped just by using the fact that my propagator is symmetric under u going to minus u. Okay. So using the symmetry. So the contribution of this big circle essentially drops in both the upper plane and the lower half plane. So we end up essentially to take the contribution of this I mean, well, I should not say like that. I mean, so ultimately we have to collect these 3 residues and whatever is the answer, that's it. So this can be easily done in Mathematica. I mean, you can collect the residues and the answer is something like that. Okay. So this is my propagator. So we are almost there now. So now all we have to do is to find the contribution of this propagator. So essentially we are interested in this kind of a figure. So this is like my boundary graviton. So all we need to know is this cubic coupling, this coupling of this boundary graviton with matter. Then essentially we can just add this to cubic vertex and we are done. Okay. So now what we'll have to do, we have to add matter to this theory. So there's this topological piece, and then there's this JT gravity. Plus 2. So there's this dilaton here. So find that. Okay. Plus, now let's say add some scalar matter. So square root g, so pi square plus square chi square. Okay. So now the first thing you see that since this matter does not couple to the dilaton, your geometry is still ADS2.
Just one question. So this epsilon 2-point function or the epsilon propagator is my graviton propagator. That's how we are interpreting. The epsilon propagator is a graviton propagator. That's how we are.
Yeah, so like the boundary graviton propagator. I mean this.
Boundary graviton. Okay.
Equal to epsilon, these are like this infinitesimal version of this boundary gravitons.
Yeah. Okay.
I mean this. Yeah. All right. So now that we have added matter, so what you see that this equation, I mean, your geometry is still pinned to ADS2, so you can consistently add matter to JT gravity. This is because now we are not exactly at the extremal throat, we are slightly moved away from it. Okay, so now you can add your matter. So its geometry is like supported to by, I mean, it's pinned to ADS2 by this geometry. So now in this ADS2 geometry, you can, so the back reaction of this matter is actually comes in the dilaton equation. Okay. So this is where the back reaction enters. And if you think of, instead of thinking of this bulk equation, as I showed that the boundary equation also captures the same physics. So if you think of this equation of motion that comes from the varying the Schwarzian action, then it becomes something like this proportional to this T matter. So the saddle actually now receives correction from this matter back reaction. Right. Okay, so here one thing I should mention that this Schwarzian, I mean, this getting this Schwarzian equation of motion. Actually, I should have said this earlier, but this is actually, I mean, it's not just equation of motion. This is actually a little deeper in the sense. How did we get this? Yeah. So this equation of motion, okay, as I'll discuss tomorrow, this in some sense invokes hydrodynamics, because you can see that this equation, I mean, which is, I mean, this equation is like Einstein's equation. Okay, I mean, there's the same equation that can come from bulk, from this dilaton equation of motion, and in the boundary, as I'll show tomorrow, this becomes something like a conservation equation. So there's the first connect. I mean, that's the first point when people started of thinking that this chaos description, this all these modes, they have a hydrodynamic connection. Okay, so we'll come back to it later tomorrow. Okay, so for the time, yeah. So this is the story. Now we are interested in this matter 2-point function. So and in ADS-CFT, so this connected 2-point functions are given by on-shell value of the action. So we have to go on-shell with respect to this JT, which has this dilaton, the metric, and the matter, which has this chi. Now, if you go on-shell with respect to this metric, then you, you get Gaussian. So this phi or set u. We have to go on-shell with of this as well, because we have to go on-shell with respect to this matter as well. Right. So now the see what we are trying to do here. So essentially, as I said, that we are interested in finding this contribution of this propagated to this matter, I mean, to the 4-point function. So for the time being, what we'll do, we first compute the 2-point function, and then we find the coupling of this 2-point function with this soft modes. Okay, then we'll join the two. So that's roughly the agenda. So that for the time being, we are only trying to compute the 2-point function, and then we'll couple it with this graviton. Okay. So now the matter on-shell action. So for example, the S matter is d2x square g del chi square m square chi square. If you use equation of motion, you can actually convert it to a boundary action. That's very straightforward for a scalar field. And that's the first thing. The second thing is that since the matter is quadratic, we can essentially compute my 2-point function from this on-shell action of this matter. So the matter is matter on-shell. Even without computing, we can easily fix it to something like this. You can actually check this indeed happens. T1 T1 minus T. So why we can do this? We can do this because although we have broken CFT2, I mean CFT1, we have still preserved some amount of SL21, right? And in SL, and is it essentially the global part of the CFT symmetry, which essentially fixes the 2-point function. Okay. So my 2-point functions for SL2 are invariant theory is still this. Okay. So now from this action, you take two derivatives with respect to the sources, you get your 2-point functions. This is something we know. Okay. So this knowledge of CFT, we can essentially fix this matter action on shell. And this chi RT is nothing but it's standard. I mean, this is like this source. But now in this case, our boundary variable is not t, it's like a t of u. So when you try to convert this in terms of u, essentially get t1 prime, t2 prime. Sorry, I call it t of u1 minus t of u2 times this IRT. This I can compactly write as T prime u1, T power so the square and this chi r u1. So in going from here to here, all we've used the fact that the z now is lambda t prime to the lambda to the power 1 minus delta t prime to the power 1 minus delta chi r t. So this we write simply as chi r u. So if you use this here, we essentially get that to this point. So now we have this action on-shell action. So we have gone on-shell with respect to metric, but there is some factor I should write, which depends on the scaling dimension. So this JTT, sorry, not right. So there's 5/60 by G Newton. There's some Gaussian derivative sitting here, plus this part. Okay. This essentially comes here and we have chi RU1, chi RU2. So now we have to go on shell with respect to this Schwarzian theory as well. But now you see that this term essentially, so let me write it, T prime U1, T prime 2, TU1 minus TU2 whole square delta. So this is like your coupling of this matter with this boundary graviton. I mean, if you linearize this TU, you'll essentially get your epsilon chi kind of vertex. But because of this coupling, now the saddle will depend on this chi RU. Okay. So TU will depend on this chi RU. And so when you go on shell with respect to TU, this part will not necessarily be quadratic. It can have higher powers depending on this delta. So simple thing is that to go to this approximation that so this Schwarzian action is actually supported by J Newton inverse, whereas this action is supported by some D delta, which for large delta goes like something like a 3 over 2. Okay. So if you approximate that your G Newton inverse is essentially much greater than delta over 3 by 2, you can drop this coupling to evaluate the saddle of your Schwarzian theory. And as before, you can just go on to compute this equation of motion from here. You find your saddle, it's fine. And you put that on shell value here, you get your 2-point function. All right. So when you do that, ultimately you can read off your 2-point function. Say the operator dual to this guy is say V. So my VU1, VU2 is essentially T of U1, so T prime U1, T prime U2. But this T now does not depend on chi. Okay, this is some function independent of chi. Equal to the power delta. So as I said, this 2-point function depends on the shape. I mean, what is your saddle and what solution for this TU, what shape you have chosen. So this matter 2-point function depends on this shape. Okay. So once we have got this 2-point function, so now we are at the final hurdle. So the quantity that we are interested is something like a VU1, VU2, WU3, WU4, graph. I will explain the terms. So it's W, U3, WU4, 7. So this is just a normalization that we even did for the OTUC. So now we have to find the gravitational correction to the 4-point function. And the way we, so yeah. So we're going to find out this correction to the 4-point function due to the gravitational coupling, where for the normalization, we are using this, for example, this 2-point function, if you choose your saddle, thermal saddle, is tan of U over 2. So there's a pi, right? Pi over beta U. Then this 2-point function simply because we should call this sad. But then it essentially becomes 1 over something 2 sine U1 over 2. To the power. Or U1 is nothing but U1 minus U2. So this is my 2-point function for this saddle, which are like these objects. Now to get this one, what we'll do, we'll put this U to U plus epsilon. Okay, so that's what I mean by graph. Now, before going to that, we must note that at the level of, so we have added 2 scalar fields, which in the bulk do not interact with each other. So this 4-point function will essentially factorize into 2-point function. Okay, so there's like we finding ultimately this coupling of this the graviton with this 2-point function. So to do that, as I said, what you have to do in this expression will essentially send my tu tan of this u plus epsilon. Okay. So when you do that, this becomes sin q12 you get a correction which is like order epsilon. That's all we want. Okay. So for example, when you keep this term and you write this in the action, it multiplies this chi r. So essentially that gives you your epsilon chi coupling in the action. Yeah.
Yeah, so wasn't the whole point of getting the 3-point vertex so that we can compute the connected component? Then why are we like separating this VU1, VU to grav and W?
Yes.
Yeah, so that's the question.
Yeah. So all we are doing is like finding out this coupling, which is given by this epsilon, this order epsilon. So similarly for the W operator, W of U3, W of U4. Oh, sorry, it also depends on say W, V, and W. Okay. So
But you already had the action, right? So isn't there a way to like deriving Feynman rules to get the 3-point vertex without doing the correlation function computation? Since you have the action, that's why
I have the action. That is right. I mean, so once I know this 2-point function, I'm just trying to see how it changes under this u going to u plus epsilon. That's it.
okay, you are saying you are finding the correction.
You can, okay, you can, I understand what you're saying. You can essentially expand it at the level of action and then read of the 2-point function. It will be same thing.
Oh, okay. That one has checked. That people have checked.
Yeah, that is, I mean, that you can certainly do. I mean, even if you at the level of action, you just send this t to that. So this is the correction that you will get. So again, you are going to take derivative with this to chi. So that will be the change of the 2-point function.
Oh, so here we are computing like the correction to the 2-point function under this interaction.
Sorry.
Means when this interaction vertex is present. So this that you are computing.
Yeah, obviously this
slide,
description is obviously
this is like
when I mean this is like for connected only.
Yeah, okay. So it's like the one loop correction to the propagator kind of. So,
loop. Sorry.
So the final.
Okay. I understand what you're saying. So that is this order epsilon square thing. Okay, so this will give like something like this. You're saying I'm not doing this.
This you're not doing.
No, this I don't need. I just need this. This my order epsilon term is enough.
Oh, okay.
What you're saying is the order epsilon square correction to this propagator, which come from this the subleading.
Okay.
So essentially, I'll do it for W, I'll do it for V, and I will just join by this. Okay.
Okay.
So that they couple, yeah, they connect to different fermions. I mean, not fermion here. So this V and W thing. So this V, W.
Yeah, I mean, typically one would think like notation it will be then VU, U1, U2, and epsilon at U3. That would be like a 3-point vertex.
No, here. So, I mean, you have a doubt that this is not a 3-point vertex? I mean, see, this ultimately at the level of action, this object will multiply this chi thing, right? So,
yeah.
So when you keep this epsilon term, that will be like a epsilon chi term. Okay. So this is like a epsilon chi term. Okay. So So we have got this two. Now let me write this V. So it's BU1, BU2 essentially. Yeah, it's given by epsilon prime U1 plus epsilon prime U2 minus epsilon U1 minus epsilon 2 tan of U1 2 by 2 times delta. And similarly for this 3, 4. Okay, so this is like a bilocal operator and it's also SL2R invariant. So when this, so if this epsilon is like a SL2R transformation of U, the coupling essentially vanishes. Okay, let's just say this. Okay, so now what we'll do, we are interested in this final, in this object. So it's VU1, VU2, gravitational is connected. That is simply given by this. Right? But here, so, I mean, okay, this also has this part I'm not writing. So what are the kind of term we have essentially in this BV contraction? So you'll have terms like a epsilon epsilon, which is the propagator, epsilon prime epsilon, and epsilon prime epsilon prime. If you look at this, you have analogous expression for U3, 4. So these are the kind of terms that you have. Now we're interested in two setup. That is, one is like the TOC. So this is going to give me VU1, VU2, WU3, WU4. And the other is the OTOC, which is like this. And these two orderings, what we are doing is
Hi. So you have written this statement that it's BVWW is BB, right? So that is true only in first order, right?
sorry.
So this statement you have written that VVWW, this connected, this is
Yeah.
equal to BB, right?
This is equal to BBS.
So that is only in first order, right?
Yes, absolutely. Because this first order epsilon epsilon, so we have to compute the correction due to the propagator. Okay. Because the propagator itself goes as, so I should have showed this earlier. Where is this? Sorry. Yeah. So here you can see this C is actually 1 over C actually goes as order G Newton. So we are only interested in order G Newton correction to the 4-point function. Okay, so this is that. So now here in this two ordering, we are essentially shifting the relative ordering between U1 and U2. Okay, so now let us look at terms which are like proportional to epsilon 2, epsilon 3. Okay, so epsilon 2, epsilon 3 is nothing but this is some G mod of U. This is a function of mod. Okay, so now for example, terms like epsilon 2 prime epsilon 3, so this will be sine of finally terms like this will be right. So these two terms behave exactly for these two orderings, but this term will change sign because of the sign function in this two ordering. Okay. So now if you compute, for example, first the TOC, it gives you factorized expressions. Okay, now this. So now, so we will now finally analytically continue. So here my ordering is like this. So the way we analytically continue is as follows. So I'll choose my U1 equal to some I epsilon 1. U2 is equal to some 0. We'll excite the Lorentzian time only with this W operators. Okay. So, oh, sorry, there's no I here. with the ordering that epsilon1 is greater than epsilon3. Okay. So this is my parameterization for this TOC. Now, if you see these expressions, now here, for example, this we have this time in this W operator. So if you compute quantities like U34, which is like U3 minus U4, the time dependence actually completely drops down. So this will ultimately give you some constant values. As we said that the time ordered correlator ultimately decomposes to 2-point functions, and after the dissipation time kind of thing, that essentially saturates. Okay. So here, this TOC is actually constant. It has no interesting dynamics, dependence on time. Okay. On the other hand, if you choose the OTOC, okay, see these two expressions we are getting different because of the sign terms, which essentially change sign under this various ordering. Okay. So now if you compute the OTOC, this becomes something big. So this is like the TOC part. This is present here because if you choose your U2 is equal to U3, these two should match. And it indeed happens here. If you choose your U2 equal to U3, and then these two terms are exactly. So for example, this term vanishes, this vanishes. Okay. So here now we have to parameterize again. So my U1 is now like some epsilon1, U2 is 0, U3 is, sorry, what was the thing that I did? Where my U2 was greater than 0, okay, sorry. But now I have epsilon U1 is greater than epsilon3, 0. So now when you do this, actually this choice doesn't matter. Once we have got this expression, this choice does not matter that much. So once you do this, your OTOC, I'm not showing the entire expression. There are things like you have to restore your time dependence. So it becomes something like there's a linear in time dependence, and there is shine hyperbolic. See how this sign hyperbolic comes very easy to see. You are essentially putting this IT in this under the sign, so that results in this. Now, if you say that my T is much greater than beta, okay, which is the chaos regime, the T is much greater than the dissipation time. Essentially, this exponential from this will dominate over this linear behavior. So this roughly will go as so. Is the argument clear? So essentially, I reproduce the fact that in the contribution from this boundary graviton essentially leads to this exponential growth in the 4-point function. Okay. So now comes the last thing, that is how do we essentially connect this picture with this this shockwave thing. And that is actually very trivial now, because see here what happened.
One question.
Yes.
Like for the XYK model, when you showed this 4-point OTOC having a maximal chaos behavior,
Yes.
that was interpreted as that in the bulk there should be like a black hole or something, right?
Yes.
But here we what?
I don't follow the SY case. I just know how one gets chaos that's in. I don't follow it in details, the computations there.
Oh, okay. But I'm saying that here you like took the JT gravity, which is like there's a kiloton which probably gives you an ADS2 boundary, and then you have ADS2 plus a matter. So we didn't have to kind of like assume a black hole in the geometry to get this maximal Lyapunov.
No, okay. So here, yeah, this thermal saddle is like a black hole, right?
Oh, okay. When you are making a thermal channel, it automatically means that the matter has collapsed.
Yeah.
Oh, I see.
So this PU equal to U is like a 0 term, but again in 2 dimensions, I mean, it doesn't matter. It's just coordinate transformation. So having the black
Yeah.
hole.
Okay.
So now relating to the shock picture, so there what happened is that these things came and they interacted here and essentially found out that this graviton exchange, the ladder diagrams, they essentially give rise to the exponential growth in this picture. Okay. So now what we are saying is that, so we have this near horizon, near extremality, is like this ADS2 throat. Sorry. Okay. And we computed essentially this boundary gravitons of this ADS2 and their contribution. So we can essentially just take this and place it here, right? This entire thing. But this, okay, this is only true near extremality. I mean, away from extremality, you do not have this still holds, but they do not have this kind of, the expansion of this physics. Okay, but at least close to extremality, we can think of that this graviton is essentially like this boundary gravitons living in the boundary of this near horizon ADS2 throat. Okay, so in that sense, both these descriptions are equivalent, but that's only holds near extremality. But anyways, JT gravity itself, I mean, captures chaos close to extremality. I mean, away from extremality, JT is not the right thing to look at. Okay. So yeah, as I said, that this generalizes to a large class. I mean, the large class of black holes close to extremality. For example, I mean, but one thing is, one thing we should note that this computation was done without assuming extremality or non-extremality. Okay, I mean, we in fact did it for a non-extremal setup. So in that case, I think Rohan wrote a paper. So in that case, you can essentially describe these gravitons at the boundary. I mean, if you put the screen not here, because here you do not have any ADS2, but still the same physics can be extracted by studying gravitons in this boundary. I don't know how these near horizon gravitons connect to that, but essentially there is also analogous Schwarzian description away from extremality, but that holds in this conformal boundary, not here. Okay. Yeah, so roughly more or less that summarizes this Schwarzian description. Yeah, I mean, I'm done for the day.
Okay, so let's thank the speaker first for his talk today. Thanks for the talk again, Avik. And now if you have any questions, please go ahead. Okay, so since I think there's no more question, at least as of now, so organizers, we can stop the recording.